So, welcome back, and I do hope as ever you and your family are keeping well. So, what we're going to look at in this video, and I'm going to be taking the work forward from a previous one I did on looking at the language of experimentation and what type of errors we have. We're going to look at how we deal with those errors mathematically when we do experiments. So the first thing we're going to look at is absolute uncertainty. And to try and explain this, I'm going to look at a simple measurement. I'm going to look at what the width of my laboratory is. So the first thing we need to know about an uncertainty in a measurement is it does have units. So you will see in a minute that when we quote an uncertainty, and you've seen me perhaps do it in other videos, I'm going to say it's plus or minus so many centimetres or metres or what have you. Okay, so we're going to ask the question, if we make a measurement, so here's our question, the actual value, so what we might call a textbook value, lies within what range? So, if I state a value for the sort of width of my laboratory, okay, what sort of range is that sitting in? Now, this is a bit difficult to explain, okay? So let's do it in terms of an example. So if I measure the width of my lab, it's quite a large one, a very old building, okay? So my lab, and the width of it, let's say it's equal to 10 metres. It is approximately 10 metres, okay? But in reality, if I got out there with a ruler and I used a metre stick, now I'm not turning it that way, okay, so I'm just using a metre stick, a stick that is known to be a metre long. I can stick it against the far wall and I can fold it over a few times and I get stuck at the far end because it doesn't quite fit in or there's a little bit missing, okay? And because there's nothing written on it, I can't really comment how much that extra or short bit of length is, okay? So what I'm doing here, if I quote the width of my lab as 10 metres, okay, this is really 10 plus or minus 1 metre. So I know the absolute uncertainty, okay? Notice it's got units, and I know that my lab could be 9 metres, or it could be any value up to 11 metres, and that's the range within which the width lies. But what you're saying is, come on, FJ, do it properly. Get out the proper metre ruler, and let's say this one has centimetre markings on it. Okay, so I now have the ability to fold it over and work out how many metres, and then I can poke a little bit of the ruler along to get the remaining bit in centimetres. Okay, so if I say that my lab is 10.23 metres, okay, what I'm saying there is that it's 10 metres and 23 centimetres. So I'm now measuring the width of my laboratory to the nearest centimetre. Okay, so this is 10 metres plus or minus. Now you've got to be careful here. I can't write 1 centimetre because that's not 10 centimetres. So it's 10 metres plus or minus 0.1 metre. Okay, now that makes me realise that when I measured the lab, okay, it could be 10.24 or it could be 10.22. Okay, it gives me the range in which the real answer lies. Now you can take this further and further and further, and you can say, what about millimetre reading? Sure, okay, and then you'll see it will be 10 plus or minus 0.001 metres. There's a bit of a problem there with you'd need an extra place here, of course, if you were measuring to the nearest millimetre. So that's a start at looking at absolute uncertainties, the fact that we can quote the range in which the real value is known to lie, even though we don't know it accurately, okay? And here, the absolute uncertainty gives us how much variation there is between our measurements and where the actual measurement lies. So let's have a look at measuring devices, the sort of things we can make measurements with. And we'll look typically at a ruler, or is it a rule to begin with? I'm going to call it a ruler. Okay, so I hinted earlier that if we've got a ruler with a centimetre scale, okay, we can argue this for ages and ages, but what we're basically saying is that we can see whether it's 10 or 11 or 12 centimetres, but we can't really say what it is in between. Okay, so a centimetre scale is going to be plus or minus 1 centimetre. Okay, but if we've got a ruler with millimetre scales, so it's calibrated in millimetres, then sure, we can see whether it is 11.3 or 11.6 millimetres. So we can measure to plus or minus 1 millimetre. Okay, so the point I'm making here is, and I'll argue this one in a minute before any of you say, but I've been told something else. Okay, if you've got a device with a scale on it, okay, we're always going to quote, the absolute uncertainty as plus or minus 1 scale width. Okay, now I'll come back to that because probably a few people going, that's not what we were taught, but I'll explain my reasoning in a second. Okay, but the point it makes is that if you're going to make measurements and you need a lot of decimal places, you need a high resolution, okay, then you've got to be careful to choose the right thing. So you're not going to measure the width of a wire or a human hair with a centimetre scale ruler. There are ways to do it, okay, but we won't worry about that. You're not even going to use a device that's calibrated in millimetres. You're going to use a screw gauge micrometer, okay, that will be plus or minus something much smaller than that. Each division on it is much, much finer, much smaller, okay. So let's very quickly deal with this. What's the sort of number that we can get here, okay? The best value for the uncertainty, okay? Well, I've said it's the width of one division on any measuring device that you've got, okay? Now, a lot of people are taught, I would say quite correctly, that it's half the width, and I'll justify that now, okay? So if you have the ruler up against something, and the thing you're measuring is here, okay, you might be able to say 1.5, 1.6, 1.7. I agree with you, okay. The thing that they miss when they say that is, if you lie something against a ruler like this and you measure to this point, you're out here at the beginning, okay. There's some uncertainty of where you've positioned it for the 0, and there's some uncertainty about where you're looking. There are 2 uncertainties that need to be added together, okay? So I would say that always choose the width of the smallest or finest gradation on the item that you're measuring, with one exception. And that exception is if you absolutely know that you're not going to get an error at the starting point. Okay, you're not going to get a 0 error as well that you need to take into account. So if you know there's no 0 error, okay, then you can do half a scale. Okay, so something like plus or minus 0.5 degrees C. Okay, and we assume that thermometers typically don't have a 0 error. Okay, so a quick look at measuring devices there, and we've looked at the resolution, the smallest scale that we can measure down to. But just before I finish on this little bit, you've got to be really careful about stopwatches, okay? Because you know that stopwatches have a resolution of about 100th of a second, 0.01 seconds, but they're limited by the person operating them. And if it's a human operating them, we have a reaction time of about 0.1, 0.2 seconds. So we can't quote uncertainties that are in the hundredths of a second region. So we are always going to say that our timing measurements for a stopwatch has an uncertainty of about plus or minus 0.2 seconds. And it's really important at A-level you pick that up because you're often asked to comment on readings that are taken with stopwatches, and please don't use lots of decimal places. Okay, you can really only use one decimal place if you're working in seconds. So let's now put what we've looked at earlier to use, and we're going to look at percentage uncertainties. Okay, so let's use a millimetre ruler, and I'm going to stop getting into the argument of is it a millimetre rule or a millimetre ruler. Okay, a millimetre ruler to measure some length. Okay, and we know that its resolution, its scale, is calibrated in individual millimetres. So we know that the smallest change on the scale is 1 millimetre. So we're going to call that our uncertainty. Okay, so we could be going to be out either side maximally by plus or minus 1 millimetre. So let's make a measurement. So we measure 3 millimetres. Okay, so what we need to do is work out what the percentage error is in this. It's really important because we're going to use percentage errors a lot later on. Okay, so the percentage uncertainty here is sort of exactly what you expect. Okay, the biggest amount we could be out by is 1 millimetre, and it's 1 millimetre in 3 as a percentage. Okay, so that's 33%. So what we're saying is our measurements could be 33% out either way of the known value. Okay, now I think you realise there that using a millimetre ruler, okay, so plus or minus 1 millimetre, to measure a short length is not a good idea, okay, because the percentage error is going to be quite high. But let's do another experiment. Let's use the same ruler and measure something that's a bit bigger. Okay, let's measure something that is 6 millimetres long. Okay, well, we know it's 6 millimetres plus or minus 1 millimetre. So the percentage uncertainty is equal to 1 millimetre in 6 of them as a percentage. Okay, and that's about 17%. So our true value, okay, will lie within a range that's 17% too big or 17% too small. It'll lie somewhere within that. Okay, so and that's our measurement. So we're saying that we got 6 millimetres for whatever we measured. Okay, but in fact it could be 17% bigger or 17% smaller than that value. Now I'd like to look at just one more example very quickly. Okay, what happens if we use something like a tape measure? And the tape measure is calibrated with a centimetre scale. Now, obviously, nothing changes here, but I want to give you an example where we use it to measure metre lengths. So we measure something on the floor, maybe, okay, a plank of wood or something like that, and we get 3.27 0.26 meters. Okay. Well, now we can do things really properly, because you can say, okay, centimetre scale, the smallest difference, the resolution of the tape measure is 1 centimetre. So this is going to be out either side, possibly by 1 centimetre too big or 1 centimetre too small. So we can quote this as 3.26 plus or minus, here we go, this is in metres. So this has to be in metres as well. The absolute uncertainty has units. Okay, 0.01 metres. Yep. So let's work out the percentage uncertainty in our measurement. And I hope you feel this is quite easy now. Okay, it's a very small amount in a largish reading, so I think we're okay using a tape measure for this. It's 0.01 metres error in the whole lot, 3.26 metres as a percentage, okay, and that equals about 0.3%, okay. So using a tape measure in this way is going to give us quite a small error. Now, later on, we're going to do some work with percentage errors, because we can add percentage errors to work out the total error when we have to do different measurements of something. We're not just doing one measurement, but we might be measuring in different directions, or even more complicated, we might be working out a resistance where we're measuring a voltage with an error and we're measuring a current with an error. So in that situation, we need to know the percentage error in both the readings that we take, so we can find a total percentage in the answer that we get. So now let's look at how we quote absolute uncertainties for experiments where we measure the same thing over and over again. So what I've done here is I've done an experiment where I've measured the speed of sound, and I've measured the speed of sound 5 times. Okay, so let's have a look at what's right about this, and then we'll look at what's very wrong with it. So we've said the number of tests we've done, yeah, 1 to 5, that's fine. We've said the velocity in meters per second, so we've labelled the velocity and the correct units at the top of the table. That's good. We've put our numbers in all to 1 decimal place, not to different numbers of decimal places. I was tempted to put 326 in here to remind you that it would be 326.0. Okay. We haven't put units in the table, which is correct. We've only put units on the heading. And then we've made a mistake. Okay. Because we look at our data set and we can see that this one here is an anomaly. Okay, now it's probably anomalous because we've probably swapped those 2 digits around. I'm not sure what I did, so I'm not going to second guess it. I'm not going to go, I'm sure it's 328.8. I've no idea what I did there. I probably made a measurement that was, I stopped the stopwatch a little bit early, so I got it going much faster than I thought. Whatever, it's an anomaly, so it's out of the question. Okay, so there are only 4 useful data points here. Okay, so let's see how we can quote the uncertainty. So we're going to quote the value that we get, okay, like this. And this is an important skill. Okay, so follow me through on this. The first thing you need to do, I think is fairly obvious, get the mean of the data. Okay, so the mean, the average, yeah, is 330.4 meters per second. Okay, so remember how you get the mean. I'm not being patronising here. You've got 4 readings that you add up, find the answer, and then divide by 4. Okay, make sure that you do not add in the anomaly and you don't divide by 5. Okay, and Again, I'm not being patronising, but it's really easy on some modern calculators to type in the first one added to the next one, added to the next one, added to the next one, divided by 5. So you made a mistake there twice. You divided by 5 and it's only 4 readings, and you've probably divided the 4th reading by 4. So add the 4 together, kind of in brackets, and get that answer, and then divide by 4. Okay, you'll know, I hope you'll know, because this will come out as a slightly silly answer. Okay, I'm off topic yet again, but when you do maths at A level, look at your answer and look, is it reasonable? Okay, so when you get the distance to the sun as 65 metres, don't write that down. It's clearly wrong. Okay, you might have the wrong units, or you might have completely the wrong number. Okay, this looks pretty sensible. So take your data set and find the mean of the data that's sensible. Okay, and then to work out the absolute uncertainty, find out what the range of the data is. So the data range, because it's interesting to know, that the mean, the normal mean, doesn't tell you that. Okay, it's interesting to know, did it vary between very low and very high, or just between quite narrow limits? Okay, so take the range, of the data. Okay, so that is 333.2. That's the largest, minus the smallest, which is 328.6. Okay, so I'm checking there, which is why I was a bit slow. Have I got the largest value? Yep. And have I got the smallest value? I was going to go for that one, but it's that one. Okay, and then take that range and divide it by 2. Okay, and I think you'll see why this is the obvious thing to do. If you do that, you get 2.3 meters per second. Oh, I get it. Okay, that there's sort of a midpoint, and the numbers can be 2.3 meters too low or 2.3 meters too high. So now you can do the correct thing and quote your value. Now this is A level, okay, so you're not just going to stick that down, because you're not telling us what the uncertainty in that is. Okay, so what you're saying is that the actual value, the actual value for the speed of sound is equal to 330.4, that's our mean, plus or minus 2.3 meters per second. Okay, so there is our correctly quoted answer from our experiment. Okay, we found the average, and we've told people who are reading about this how much the actual value could vary from that within what bounds. And you'll notice this and this are to the same number of decimal places. There's some argument about how you do this, but this will do. Okay, and the units are the same for both, and the units go at the end. I have seen people put units here as well, which is definitely not something we agree to do. Okay, so there you go. If you're making multiple measurements of the same thing, common one at A level is the diameter of a wire. You measure it here, 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 and here. Quote the diameter of the wire and its absolute uncertainty. So there we go. Okay, you find the mean, you find half the range, and so you can quote the mean plus or minus half the range. And obviously, if you did 2.3 of 330.4 times 100, that would be the percentage uncertainty. So now let's look at whether our experiment was any good at all. Okay, so I've calculated the percentage uncertainty, and you should be happy how to do this now. It's a really important thing that you need to know at A level. Okay, so our uncertainty, our absolute uncertainty, was plus or minus 2.3 meters per second. So 2.3 of the value that was our average times 100 is 0.7%. So there's a variation either side of the mean. We're sort of suggesting of 0.7%. So we didn't do badly there. But, okay, what's important is how did that compare to what the textbook says, what the known value is in similar situations? And you get quite a lot of this at A-level. So I'm going to sort of ask, how good was our experiment? In other words, how does it compare to what we really were meant to be reading? Okay, so we were fairly certain of our result, the result that we got. Okay, but how does it compare to a textbook value? Okay, well, I'm going to suggest, for the sake of what we're doing here, that the data book or the textbook, has the speed of sound. It gives the speed of sound as 348.8 meters per second. Okay, so that's in air at a particular temperature, humidity, and pressure. Okay, I've kind of just sort of gone for that number for the sake of the demonstration. Okay, so this is an important idea. What we're going to do now is compare that value, the textbook value, to the one that we got with our experiment. Okay, and the way you do this is you take the textbook value and you take it away from your values, and you divide that by the textbook value. Okay, now there's another way of saying this with respect. Okay, should we say that that's the best measurement and this is the worst because it's ours? Okay, so another way of thinking about it is best minus worst. Okay, so that gives you some idea of how far out we are from the textbook value. Okay, we're kind of hoping that that comes out as 0, but it won't. Okay, best minus worst over best. Yep. So let's do that then. So the textbook value is 348.8. Take away our value, 330.4. Okay, so that's the variation from the textbook value, divided by what it should be. Okay, 348.8. Okay, multiply all of that by 100%. You'll see why when you do the maths on your calculator. And this comes out as 5.6%. So, what you can conclude from that is your experiment went really well, in fact. The reading that you got with the equipment you used was within 5.6% of the known textbook value. Okay, and this is the sort of thing you might be asked to comment on at A-level. How good was your experiment? And we use more technical terms, in fact. But this has gone really well. Okay, if that was something like 60%, I think you'd be worried. Okay, so we've used our percentage uncertainty measurements now to compare how our data was. Was there a big spread in our data or not? And then when we've got our mean, we've compared our mean to a textbook value and seen what percentage it varies from the textbook value to see how good our experiment was. So let's quickly look at how we quote an uncertainty when it's not actually given to us. We've just got a single value. So this is when the uncertainty is not stated. Okay, well, this is fairly easy, in fact. So, for example, if we're given a measurement like 1.2 meters per second, okay, we can see that it's been measured to the nearest tenth of a meter per second, so we can say that that's our uncertainty. Okay, this could be a little bit bigger than 1.2 2, and it could be a little bit smaller than 1.2. So we'll quote our uncertainty in this form: 1.2 plus or minus 0.1 meters per second. Okay, so we look at the sort of finest precision that it's been measured to and take one of those units, unless we've got a good reason not to. So, for example, if we measured a voltage and we got 3 volts and the uncertainty in that voltage was not quoted, we can see that there are no decimal places here, so we can say the absolute uncertainty is 3 plus or minus 1 volt. So finally, let's have a look at how we quote uncertainties. If we've got multiple measurements in the same units, but not of the same thing, okay? And we're going to add together the numbers that we get to get the value that we want. Okay, what I mean by that is, just imagine you're going for a run and you run 6 meters this way, plus or minus 1 meter. Okay, so there's the uncertainty. You run this way, 5 meters plus or minus half a meter, and then you run that way, 7 meters plus or minus 1.3 meters. Okay, so how would you quote the distance that you've run, including the absolute uncertainty? Well, I guess it's pretty obvious in this case. What you do is you add together the distances that you ran, okay, and you ran 18 meters. Now, it's interesting here that we've got 1 decimal place, 1 decimal place, but here we haven't got any with 6. So we're going to leave it at 18, okay? And then all we do is add together the uncertainties. So plus or minus 2.8 meters. But if you remember, we're here to the nearest meter, so then quoting an uncertainty to the nearest tenth of a meter doesn't make sense. So the distance that we actually did should be quoted as 18 plus or minus 3 meters. So you can see that the uncertainties here just add up to give us some idea of how far we ran. Yeah? Was it less than 18 or was it more than 18? But we know that it sits within a range of 3 more or 3 less than 18. So let's now look at how we work out uncertainties when we've got multiple measurements of different things. So instead of measuring the same thing over and over again, in this case, we're going to work out the volume of some kind of cuboid. Not drawn to scale and all of that here. Okay. Now, we don't measure the volume of this, we calculate the volume. And as good A-level students, you'll appreciate that there will be an uncertainty in each dimension that we measure, X, Y, and Z. Okay, so I've been slightly sort of facetious with this example, but I'm making a point here. Okay, so we know that across here it's 6.2 centimetres, but there's an absolute uncertainty either way of 1.0 centimetres. Okay, I've done the same for the sort of depth, 8.3 plus or minus 0.6 centimetres, and for the height, 5.2 plus or minus 1.0 centimetres. Okay, so we know what the uncertainties are. Yep, the absolute uncertainties. So we know that these figures can vary between 1.0 centimetres bigger in this case or 1.0 centimetres smaller. So there's a fluctuation in or sort of a range of that our data could sit within. Okay. And I've worked out the percentage uncertainty here. Okay, so you remember how to do that. 1.0 divided by 6.2 times 100. 16.0% uncertainty, 6% uncertainty, and 19.2% uncertainty. Okay, so if you think about it, our volume is going to have a very large uncertainty because we're out, or at least there are some unknowns in the actual values. So let's look at how we deal with that. How can we quote a volume of this with an uncertainty? Okay, because multiplying these numbers together will not give the exact correct volume. Okay, so the first thing to do is to work out the volume. So this is what we do. So the volume, just by multiplying the three dimensions together, is equal to 267.6 centimetres cubed. So there's a couple of things going on here. One of them is we've got the same number of decimal places, and we're not forgetting to put the correct units on. Okay. But what are we going to do now with our uncertainty? Okay. Well, what you do in this case is, because we've got an uncertainty here and here and here, we add the uncertainties. So it's a length times a length times a length. Okay, so I'm sort of suggesting that the volume comes from length cubed. Okay, and if you times one thing by another, you add the uncertainties. So we will add the percentage uncertainties. Okay, now what's really important is you don't add the absolute uncertainties. You can't kind of add centimetre to centimetre to centimetre, because if you did, in this case, you'd get units of centimetres and not centimetres cubed. So take the percentage uncertainties, add them together, and you should get an uncertainty here of 41.2%. Okay, so that's a huge uncertainty. And now you can work backwards. Okay, so you could say, okay, we know the volume, yeah, and there's a percentage uncertainty of 41.2%, or we could work out the absolute uncertainty. So 41.2% of our volume, 267.6 centimetres cubed, yeah, is equal to 110.3 centimetres cubed. So what we can do is, now we've got our absolute uncertainty, we can quote the volume as being what we calculated by multiplying the sides together. Okay, so 267.6 plus or minus 110.3, and there's our units, centimetres cubed. So you can probably see here that the compounding sort of error, as it were, caused by the uncertainty is quite important when we get our volume number. So the main thing to take away from this is, if you are doing maths which involves uncertainties where we're multiplying together, work out the percentage uncertainty in each value that you're going to multiply and add those uncertainties to get the total percentage uncertainty, and then you can back calculate to the absolute uncertainty. So, in summary on this point, just to make it fully clear, imagine you're doing an area, and it's an area of a circle. Okay, so this is a common one, pi r squared. Okay, so if you think about that, that's pi r r, so the r is coming up twice, it's multiplied together twice. So looking at that power there, you know that if you've got an uncertainty, you need to double the percentage uncertainty when you quote an area. Okay, now we don't bother quoting an uncertainty in pi, but the uncertainty will be from the measurement of the radius that you did, so make sure you double it when you quote your area. But what about if you do something like the volume of a sphere, of a football? So volume, 4/3, which is just a number, pi, just a number, r cubed. Well, I think you've got it now, haven't you? That if you know the uncertainty in the measured radius, what you need to do here to work out the uncertainty in the volume is you need to triple the percentage uncertainty that you had in the radius measurement. Okay, so that's something to look out for at A-level, and it comes up quite a bit. But in the case I've just done, you'll agree that the radius is in the same units, so it's a radius times a radius, or a radius cubed. But what happens if it's a formula like this one? So the force pulling something in as it rotates round, maybe the force on the Earth holding it in orbit around the Sun, the centripetal force. So F is equal to mv squared upon r. Okay, now don't worry too much about the physics behind the formula, but there's a force, okay, and if you have to calculate that force, you're going to have to take a mass and multiply by the velocity squared of the mass going round and divide by a radius of orbit. Okay, so this is quite a tricky one, and again, I think you probably guess what you do here. Okay, to work out the error in the force, so the error in F, or the uncertainty in F, what you're going to do is you're going to work out the percentage uncertainty in M. Okay. You're then going to work out the percentage uncertainty in V, the velocity. Now, that might be got by adding two percentage errors, because remember, a velocity is meters per second, so it's a distance divided by a time. Okay, but if you know the uncertainty in V, in this case, because it's V squared, you need to double it. And even though it's divided by the radius, okay, you still work out the percentage uncertainty in R, okay, and to work out the error, or more correctly, the percentage uncertainty in F, in other words, how much either side of the mean value it could be, okay, you add the uncertainty in the mass added to the uncertainty in the velocity and the uncertainty in the velocity again, so double the velocity, okay, added to the uncertainty in the radius. Okay, so the dividing makes no difference here. You just add, and add again, and that will give you a total uncertainty in F, the force. Okay, finally, just to really push the limits, let's do one from electricity. And it's exactly the sort of thing you'll have to do at A-level when you do experimental work. So there's a formula at A-level that you'll come across that says the resistance of a material, okay, is equal to a constant about it, rho, the resistivity, multiplied by how long it is and divided by its cross-sectional area. Okay, so you don't need to really worry about what's going on here in the maths, but you can see that there's a calculated value that is calculated from 1, 2, 3 things there. Okay, but you're normally asked to work out what this one is. Okay, so let's rearrange this equation for rho. So rho is equal to RA upon L. Okay, so the resistivity is the resistance multiplied by the cross-sectional area of the object divided by its length. Resistance. Oh, crumbs. You're probably not going to measure resistance directly. You're going to calculate it from potential difference in current. And you remember that resistance is, I'll say it badly, volts divided by amps. Potential difference divided by current, or V over I. Okay, so we've now got rho is equal to V over I sort of times by A upon L. Okay, you don't really need the times sign in there. You can just put VA upon IL. Okay, so I hope you can see what we need to do here to work out the percentage uncertainty in this value, the resistivity rho. Okay, it's going to take me a while to jot all this down, but the percentage uncertainty in that one is going to be equal to this one plus this one plus this one plus the percentage uncertainty in that one. Okay, so I hope you can see what we've done again is we've worked out the percentage uncertainty in each of these values that we've measured, and when we know those, we add them all up, and that will give us the total percentage uncertainty in the value that we calculate. And then you can turn that back if you want into an absolute uncertainty. So work out the percentage of this and then say plus or minus that much. So I'd like to do one other quick example just to make a clear point about how we add uncertainties in formulae. So imagine we've got this formula in physics. I'm not suggesting this is something that we'll do. I'm just pointing out that there could be a formula that is this. Okay, I'll put a times sign in there, root B. Okay, so we want to calculate y from A and B, which are measured values, and we want to know what the uncertainty in y is if we know the uncertainty in A and the uncertainty in B. Well, I hope you feel confident about the uncertainty in A. What you do here, is 3 times the percentage uncertainty. Okay, and then we've got to deal with the uncertainty in B, but you'll notice it's root B. Okay, so it's kind of B to the power a half, and there's the hint. Okay, because of this square root, we take half of the percentage uncertainty. And so now we've got the uncertainty in A 3 times over because it's A cubed. We've got the uncertainty in B halved because it's B to the power a half. And so if we want the uncertainty in Y, so the uncertainty in Y, it will just be 3 times the uncertainty in A added to half the percentage uncertainty in B. So I hope you found that video useful. It's not an easy topic, and I think you probably need to go back and pause the video and have another look again. But I've done my best to try and explain how we deal with uncertainties at A level, and you can be pretty certain that it's going to come up. So I hope you enjoyed that video. I'll be making another one soon, and I look forward to seeing you then.